So first of all, I would like to thank the organizers for all their effort to make this experience really enjoyable and really convenient for everyone. And it's very exciting and an honor to give a talk here at Amplitudes in Seoul. Yeah, I'm going to explain how to write systems of linear PDEs in matrix form, and I need a presenter as well. So that itself would not be new to you, of course, but I'm going to explain how to do that with the help of Gröbner bases in non-commutative algebras of differential operators. So we're going to look at so-called holonomic functions, let's say in n variables, and those are functions which are solutions to a sufficiently large, namely a maximally overdetermined system of linear PDEs with polynomial coefficient. Various functions are holonomic, like a lot of special functions, hypergeometric functions, also Feynman integrals, and you can cook up many more from those. And we're going to look at the linear PDEs that these functions fulfill. They occur mainly in two shapes. One way to write them is really to write them as a system of homogeneous PDEs, as you see on the left-hand side. It's a finite sum, and f to the beta denotes a mixed partial derivative of f, and the c's are complex coefficients. Or you might also write them in matrix form, where you write them together as one equation, where now A is a matrix of differential one forms, and capital F is a vector of functions, in applications typically a vector of master integrals. And what I'm going to explain today is how to pass from 1 to 2. So I'm going to explain how to write, really how to compute these connection matrices A, starting from a system of linear PDEs. We want to do this systematically, and for that we use the field of algebraic analysis. This studies linear PDEs with methods from algebraic geometry by encoding them as D modules. And this provides really foundational contributions to the theory of PDEs, but it also has a strong computational flavor. And to do that, we need Gröbner bases. This is how really software would compute with D modules. And we're going to do this in computer algebra software to be able to carry out symbolic computations in contrast to numerical computations. So this talk is going to be about a package that I wrote with Paul Gerlach, Joris Köfler, Maru Zairafi, Hendrik Schröder, my PhD student Nicolas Weiss, and Francesca Zaffalon. That's a package in Macaulay 2, not in Mathematica. Let me stress that's one standard software for computations with polynomial systems. And an important point is also that it is open source. So let's look at rings of differential operators. Again, f denotes a function of n variables. And if we have a linear PDE that f fulfills, I would instead encode it as a differential operator, like as a sum as you see on the right-hand side. And the notation I'm using is, well, if you start from a differential operator, the associated PDE is, I would write p bullet f is equal to 0 for that. So the application of the ith partial differential operator to f gives the ith partial derivative of the function. Just as an example, if you look at Airy's differential equation, it's an equation where one observes Stokes' phenomenon. This would be encoded by d squared minus x. And now if we collect all these differential operators in a set, this gives a C algebra, in particular also a ring. So you can think of them as polynomials in the x and d variables, but it's important in which order you write the x and d down. It makes a difference if you first multiply a function by x and then take a derivative, or vice versa. But it's a non-commutative ring, and the generators obey the Leibniz rule, and in algebraic terms, it reads that the commutator of di and xi is 1. Okay, we're going to look not only at single differential equations, but at systems of such, and these correspond to ideals in the Weyl algebra. These are subsets which are closed under addition, and we want to impose that they're closed under left multiplication by elements of these. So we're going to look at lefty ideals, and the notation I'm going to use is as such. And now, if you have a left the ideal system of PDEs, you might look at its analytic solutions. And it turns out that left the ideals encode crucial properties of their solution functions, such as their singularities, and we're going to hear more about that in the talk of Felix Tillander, their growth behavior, and also the number of data that you need to uniquely encode the function and pass it to a software, for instance. I want to be a bit more specific about that. Let's look at some examples. The annihilator of F is the subset of the Weil algebra consisting of all differential operators that annihilate the function. And this is a left ideal in the Weil algebra. Just a very simple example, the annihilator of x to the n. Well, x times the derivative of it is n times the function, so x minus n is in the annihilator. But also the n plus first derivative vanishes. And this is indeed the full annihilating ideal in the Weil algebra. If a sum of Euler operators minus a scalar k is contained in the annihilator of a function, then one can conclude that the function is homogeneous of degree k, and also vice versa. And one more example is that the invariance, or one might also call it symmetry under the conformal group, is encoded as being the solution to a certain D ideal, also known under the name of word identities. Okay, so far we had PDEs with polynomial coefficients. We will also need a slight variation of that. We also want to be able to divide by polynomials. So we're also going to look at differential operators with coefficients in the field of rational functions. And the resulting ring of differential operators, this is called the rational Weil algebra, denoted Rn. Looks very similar, and indeed, if you're interested only in analytic solutions to your PDEs, this does not make a difference. But the algebraic and geometric differences between an ideal in the Weil algebra and the ideal considered in the rational Weil algebra, they are very subtle. Yes, there's one important number that we're going to meet. This is the so-called holonomic rank of a D ideal. And for this, we're going to consider the quotient of the rational Weil algebra by I. So we want to identify two differential operators whenever the difference is contained in I. And this is a module over Rn, but in particular, it's also a vector space over the field of rational functions. And its dimension is the holonomic rank of the D ideal. Generically, the rank of I gives you the dimension of the space of analytic solutions in a small neighborhood around this point. And this will also be the size of the connection matrices. And for a single ODE, this simplifies a lot. So if we have a n is equal to 1 and a D ideal generated by a single differential operator, the holonomic rank is just the order of the differential equation. It's also the size of the companion matrix. Yeah, and I brought a friendly example that we'll see later again. Let's look at this. The ideal in two variables, it's generated by two differential operators. And if we look at this quotient here, let's think about what do we need as a basis to span or to generate this vector space. For sure, we need 1, D1, but we won't need D2. In the quotient, we can express it in terms of 1 and D1. And you can argue similarly for mixed and higher derivatives. So 1 and D1 is the basis of this quotient, so the holonomic rank is 2. The system of equations will have two solutions, and you're invited to think about the solutions. We'll come to that later. And from this D ideal, one can also read the so-called singular locus of the D ideal. It's the variety, like the vanishing set of this polynomial. The subset of C2, and also tells you where solution functions might have singularities. And singular locus can really be computed purely algebraically from the D ideal. Okay, we have now all ingredients to really write a D ideal in matrix form. So let's say we have a D ideal of rank M, and we choose a basis of this quotient, denoted by S1 to Sm. And whenever we have a function which is a solution to I will denote by capital F this vector here. Like I apply the basis elements, they're polynomials, or you can choose them to be the monomials in the partial. And I will apply them to a function. So this would be the function and mixed derivatives of it, or linear combination. And now by linear algebra argument, there exist unique matrices A1 through AN such that the ith partial derivative of f is a matrix multiple of the vector. And this identity will hold true for any element in the solution space of I. Yeah, these connection matrices do not quite commute, but they fulfill the integrability conditions, which read as such. The commutator of AI and AJ is this difference of the partial derivative of the matrices. And well, let me stress this point. Like you might choose a vector of master integrals for capital F. From my computations, I would choose a function and mixed derivatives of it. So we need to think also what happens if we carry out a base change. And if we do a change of bases with an invertible matrix entries and rational functions, the transformed system reads as such, but the transformed connection matrices are the gauge transform of the original ones. Yeah, geometrically, these matrices really arise from a vector bundle with an integrable or flat connection after choosing a basis. And to compute them systematically, we will use Gröbner bases in the rational Weil algebra. And dually, if you prefer that, you might also write your connection matrix, instead of having n of them, you might also write them compactly as a matrix of differential one forms, and to pass from one of the other with some dualizing hidden for the sake of this talk would be this matrix here. Yeah, and in physics, in dimensional regularization, the epsilon factorized form is particularly popular. So you would like to find a basis such that the epsilon factors out and your connection matrix is independent of epsilon. Okay, let's look again at our example. Maybe you found in the meantime that these two functions here are solutions. They span the solution space through the DID. And you can check that whatever solution you pick, if we write f and d1f in a vector, then they will fill the set of matrix differential equations or compactly together this equation of differential one forms. Okay, this you can just easily compute, of course, but today we want to do this systematically with the help of Gröbner bases in the Weil algebra. And well, if you work with linear equations, you use a Gauss elimination to simplify it and solve it. If you have a polynomial systems, Gröbner bases are the thing to deal with these systems. And I would first like to just to give you a bit of an intuition how it works in the commutative, in the classical case of polynomial rings. Let's say we have an ideal in a polynomial ring and we want to study its algebraic variety, and that's the common vanishing set of all polynomials contained in I. And I also brought an example here. You see a parachute diagram, and you can, well, compute its graph polynomial. And what you see on the right-hand side, this is the real vanishing set of this polynomial. It's an algebraic variety that I took from a collaboration with Claudia Febola. But now the point is that ideals can be presented in various different ways. You might write it to be generated by polynomials P1 through Pk, or by another choice of polynomials Q1 to QL. So that's by far not unique how you present an ideal. And in the Weil algebra, that's maybe even more surprising. In the Weil algebra in 4 variables, you might look at the d ideal generated by d1 through d4. You can equivalently write it to be generated by d1 in this longish operator. Well, if I look at it, to me, that's not obvious. And now, what are Gröbner bases? They are particular generating sets. They depend on the choice of a term order. So whenever I give you a monomial, a polynomial with one term, whenever I give you 2 of them, you want to be able to decide which one of them is larger. And a term order, yeah, this is a An example of that would be, for instance, the lexicographic order, where you really order them like alphabetically. And now Gröbner bases, they are used, they make ideals comparable. You can read properties of ideals, and most important, you can compute with them. Let's say you want to solve a system or carry out a geometric projection for a variety and so on. Good. There's also a counterpart of Gröbner bases in the Weil algebra. So we will write each of our differential operators in this form. And we will also need to choose a term order in the Weil algebra. The monomials that we now consider, they are of this form, x to some power, d to some power. And yeah, a term order is a total order on the set, together with some technical assumptions, adapting to the non-commutativity and making like Buchberger's algorithm and so work. An example that we'll use later is of the following form. Let's say we choose a positive vector v, and this is the weight we put on the partials. And we first compare the weight of a monomial. So we put weight 0 to the x variables, weight v to the d's. And in case the weight of two monomials coincides, we use the lexicographic order as a tiebreaker to decide which of them is larger. And this defines an elimination order on dn, which means that if we multiply by a power of x, this will not have an impact on the relation order between monomials and the d's. Okay, that's a bit technical, but we need that. So the initial monomial of a differential operator is now the monomial which is largest for the chosen term order. And the initial ideal of a d-ideal, this is the ideal which is generated by all initial forms of your ideal. And just as a warning, it's in general not sufficient just to take the initial forms of arbitrary generators. You really need to take the initial forms of all elements in your ideal. But if it is true that your generators generate the initial ideal, then you say that your generators are a Gröbner basis of the d-ideal. The monomials, which are not contained in the initial ideal, this is what is called the standard monomials, and these we'll use later to cook up the counterpart of master integrals. In our example from before, let's say we choose the weight vector 1, 2. And then here, if you want to decide which of the monomials is largest in each of them, well, this term has weight 4, so that's the winning term. Here we have weight 1, 2, 0, so that's the winning term. But they do not generate the full initial ideal. You can compute that a Gröbner basis would, for this term order, would be well, consisting of these 3 elements here on the bottom. Okay, and this we're going to use to compute connection matrices. So I explained you what term orders in the Weil algebra are, and if we restrict such term orders to term orders in the partials, this gives a term order in the rational Weil algebra. The monomials are now just monomials in the D's, because we want to consider Cx as our coefficients now. Yeah, and the standard monomials of a Gröbner basis of R and I, they are Cx basis of the quotients, and they will be an equivalent choice of basis or equivalent choice of master integrals in applications. Yeah, and to compute now really connection matrices, one proceeds as follows. Let's say we have a system of PDEs encoded by I. We compute a Gröbner basis G, and we compute the standard monomials. The first one can be chosen to be 1, and we have a couple of other monomials in the D. And remember, we were collecting these terms in the vector F, and we are interested in computing such a system. So what we need to know is what is the I times Sj? And each of them can be written as an operator which is contained in our ideal I, plus something which is not contained in it. So that's a linear combination of the S. And by that you can read that the small a's, they are really the entries of the connection matrices. And to compute them, we need to do a reduction, like a division with a remainder in the rational Weil algebra. And this was the main step. So we needed to compute we needed to compute so-called normal forms in the rational Weil algebra. But we were running into a small problem. The rational Weil algebra or Gröbner bases in there were not implemented in Macaulay 2. Gröbner bases in Dn are implemented there. So the workaround that we were using is the following. To compute Gröbner basis of the ideal in the rational Weil algebra, we computed a Gröbner basis of the D ideal I. And then for specific term orders, namely elimination orders, which allow you to eliminate the contribution of the x variables, this also gives you a Gröbner basis of the ideal in the rational Weil algebra. Okay, and we had, there are algorithms for this reduction, and we had to do a small modification to the rational Weil algebra. Yeah, so if you're interested in the package, you can find it at the math repository of NPI Leipzig, and you're very welcome to try it out on your favorite example. So if you manage to push it to the limit, we'd be very happy to hear about that. And I here wrote the code that you can use to reproduce the example that we had on the previous slide. And this was, of course, a bit easy and boring. You can solve it by hand, but it fitted on the slides. You can find more interesting examples in the documentation, like a classical example of the Gauss hypergeometric function, or we also reproduced computations for a mass S1 loop Feynman triangle integral, and you can conveniently change bases, carry out gauge transforms. And we also visited a cosmological correlator for the two-side chain. You'll hear more about differential equations behind such functions in the talk of Lydia on Thursday. And we also reproduced the gauge transform to really arrive at an epsilon factorized form. Yeah, and with that, I would like to conclude. So in my talk, I tried to make the point that algebraic analysis really provides a tool for the systematic, first of all, investigation, but also manipulation of systems of PDEs behind holonomic functions in the sciences. Thanks a lot for your attention.